Welcome back to 4.2, dealing with patterns and linear functions. In the first section, we saw the basic understanding of graphing, dealing with types of graphs in the real world. As we start to segue into where we'll see patterns with numbers and linear functions going in a straight line, a little bit of vocab here to start off. So in a relationship between variables, the dependent variable changes in response to another variable, the independent variable. So in terms of math, values of the independent variable are called inputs, so the x values of the dependent variable are called outputs. So values of the independent variable, so independent implying the input, that's a good way to think of it. Input, independent, both begin with in. So when we put something in for x, it's independent. We can put in whatever we want, but we'll get some output for y. And so we see with some circumstances, this is important because ideally, if we put something in, get something out, it can depend on what we put in. In this example here, we're seeing a relationship between the number of squares in a pattern and the perimeter of the figure. If you need a refresher, perimeter measures the distance around a shape. Represent the following in a table as ordered pairs, in a graph, in words, and in an equation. So we're doing a lot here, so let's take this one step at a time. So we have the visual here for different squares when we're adding on more squares. So let's take a moment first to talk about when we're dealing with just one square. In this scenario, what's the perimeter of this going to be for this one square? Well, if we walk from here to here, that's 5. Here to here, that's 5. 5 again, 5 again. So we have 4 versions of 5, which is going to say that our perimeter is 20. Okay, well, that's something we could graph out. We know that if we have one square, the outcome is going to have to be 20. So we can easily graph out this as an ordered pair of 1, 20. Cool, so we got that one. Next one, if we have 2 squares now, let's check this out. So keep in mind that we're walking the perimeter. We're walking on the outside. So in this case, we have this 5, this 5, this 5, this 5, this 5, and this 5. What's this new perimeter going to be? Got 6 versions of it. So it's as if we have 6 versions of 5, which is really just 30. So we can say that if we have 2 squares now, this is going to be taking an approach of 30 for the perimeter. So we can graph that out. Cool. And ideally, this is going to continue in this pattern. So just as a guess, without even counting, what do you think this next one's going to be? What's the perimeter now if we're dealing with 3 squares? Hopefully you're saying 40. Because you'll notice that there's a change here of 10. We keep just moving up 10. Every time we add a square, we move up 10. So we can say that this is going to continue. If we have 4 squares, we could just count them out, but I'm confident that this is just going to be 50. If we have 5 squares, this is going to head to 60. And these are all ordered pairs we can graph out. So we'll graph out 340, we'll graph out 450, 560, and we'll eventually start to work backwards and make an equation for this. So we know that if we have 3 squares, that's 40. We'll only show 4 squares on this. If we have 4 squares, that's 50, so that's about here. If we graph this out, we see that we're kind of moving in this direction. Of course, use a straight edge when you do this. And so what do we need to do? We filled in the table, that's done. We did ordered pairs, that's seen here. We graph this. In words, we can say that this is going to continue to add 10 to the perimeter. So this, each square adds 10. And to the perimeter. As far as an equation goes, oh, sorry. Yeah, there we go. So as far as an equation goes, if we work backwards, it's as if we are eventually starting at 10. So that we could say that no matter what, we have to start with 10 units. So if we're talking about the number of squares, no matter what, we at least have 10. And then for every square, we're adding on 10 more. So we could say that this is 10x, which makes sense because if we have one square, 10 times 1 plus 1 has to equal 20, which is right. If we had 2 squares, this would have to be equal to 30, which matches the data point. So a lot of information just based off of what's going on here. And so the independent variable would be the number of squares. The dependent variable would be the perimeter. Just to relay back to that. We can also come across what they call a function, where this is a relationship that pairs each input with exactly one output value. So on the previous example, we would only have one situation where the outcome was 20 as far as the number of squares, so that's an example. We won't see this again where another output has to be 20. And so we also introduced the idea of a linear function, which is a function whose graph is a non-vertical line. So we see these two. Main idea here, we'll soon see what's going on with this. So the table shows the amount of water Y in a tank after X minutes of being drained. Is the relationship a function? Describe the relationship using words and an equation. So we see that at the beginning, this tank has 440 gallons. As 1 minute passes, let's see, how does this change? This starts at 440 and then goes down to 428. So this is a change of 12 units. We see this again here, deducting 12 units, deducting 12 units. And this is going to ideally continue as this moves. So the question asks, is this relationship a function? Does each input value have exactly one output value? You can say yes. We have no repeating x values here. They're just seen one time. Describe the relationship using words and an equation. Well, no matter what, we're starting with 440 gallons. And then how much do we deduct? How much is being deducted here? Hopefully you're saying 12x, where the output is just y. It's the number of gallons. So x in this case is minutes. Y is the number of gallons. And we can assume that this continues. As far as talking about this in words, let's say, well, we start with 440 gallons of water, and we keep deducting or keep losing 12 gallons per minute. Pretty simple sentence to think out. It makes sense in the context. And that's what's up with this section. We're seeing a lot with graphing, starting to take this towards higher level thinking, determining equations and whatnot. We'll see more of this in the next video and also the next few sections. This next example is pretty easy to understand. We're being asked to decide on the set of ordered pairs representing a linear function or not and explaining. So we are being asked to decide on pretty much if this is going to go in a consistent pattern as this moves. So let's map out our x terms here, which would be 0, 1, 3, 1. We'll go in higher order. 0, 1, 3, 1's repeating, so we'll just keep 0, 1, and 3. As far as the y terms, we have 2, 4, 5, and 8. Pretty easy to just map this out. Although we're being given the terms as ordered pairs, we might see them here mapped out like this, where we're pretty much just going to map out what's said here, where when x is 0, that correlates with 2. So we draw arrows from our x values to our y values. Next point saying 1 to 4. Next point saying 3 to 5. Finally 1 to 8. And so if we look back at the definition for what a function is exactly, this is saying that each input value has one output value. So each input has one output. So in this case, do we see any x values that have two lines going away from it? Or do we see any repetitive x values here? Hopefully you're saying that you see 1 here and also here. Since this has two arrows leading from it, it's saying two different outcomes based off of it. So we would say that this is actually not a function. The reason that is because 1 is an x value and it's repeating, meaning that there are two outcomes based off of that. And that's really it for questions like this. You're just deciding on if x values are repeating or not.